And in the first session is very, I'm very happy to introduce Professor Zhilan Feng from the Purdue University, and she's certainly an expert, internationally well-known expert on mathematical epidemiology. And recently she has collaborated with Carlos and Fred on the classical book on modeling infectious diseases. Also, she works for the NSF mathematical biology program. So today, again, so it's very, very nice to have you to give the first talk. So the title is long, analysis of a serological series of antibodies of SARS-2 and so on, right? So welcome, Zhilan. It's your turn.
Thank you, Squay. Thank you for the introduction and for inviting me to speak here today. So a lot of the examples I mentioned today are all joint work with John Glasser from CDC, and he actually is here. I'm very happy. So in case there are questions from the audience about this serological data or any other questions, and John can help me. I'm very happy to be here. I'm sorry I couldn't be there in person to celebrate Gail's birthday. But it's very nice to be able to be part of this celebration. So the title is long, as Squay mentioned, but actually I will not be able to talk a lot about this particular application to the US using the data, serological data, because this will need to be cleared by the CDC and has not been cleared. So I will present some examples of the method and a modeling approach to other examples, just to demonstrate how this method can be used. And the actual work will submit to the special volume, the JMB volume, in honor of Fred, edited by Jianhong and Squay and other editors. And so if you're interested in this particular application, you can maybe, when the paper's out, ask me, I will send you the PDF. So an outline of this talk, first mention the importance of considering modeling that involve both age structure and location, spatial structure. And we know that models should be as simple as possible. So in most cases, we should consider simple model first, but in some other cases, simple models may generate misleading or even wrong results. In that case, we'll have to really consider more complicated models, particularly meta-population models that structured with either age or location or both. And then for those models, it can be more challenging to analyze, including the derivation of the reproduction numbers, the basic reproduction number or the effective or control reproduction number. And for this particular application, I will present today, we are more interested in vaccination as a control measure. And then we'll talk about how the reproduction numbers can be used to identify the best vaccination strategies. Basically, you want to identify the target subpopulations, either certain age groups or spatial locations that can be, in the true sense, the optimal or the best strategies. Either given certain number of doses, you want to minimize the reproduction number the most. And in most cases, when reproduction numbers are reduced, either basic or effective reproduction numbers, if those numbers are reduced, then the outbreak, the severity of the outbreak or endemic level can be also reduced. And particularly, we'll consider this gradient approach. I will present in more detail to identify the optimal allocations of the vaccines. So first, why, just a simple example, why we need to consider more complex models. The heterogeneity is one example, and here, for example, if we have a simple SIR model, right, homogeneous mixing without any subgroups, and then you can consider this reproduction numbers, either basic or control reproduction numbers. You want to reduce through control measures, you want to reduce the reproduction number to be below 1, which may lead to the eradication of the disease. And if you do that, so here I list a couple of examples. So if you have a homogeneous population, so you say you have a mixing or contact rate A, and then the probability of infection per contact is beta, and then gamma is the recovery rate, and the mu is the death rate. So 1 over gamma plus mu will give you the average duration of the infection period. And so this quantity, beta A over gamma plus mu, will be the basic reproduction number. And if you consider vaccination, suppose that a P proportion of the population that would be vaccinated or immunized, then the effective reproduction number will be given by the product of the basic reproduction number multiplied by the proportion of the population that's still susceptible. Right. So if you solve this inequality, say let RE be less than 1, then you get this threshold quantity PC, critical value of the proportion of population immunized. So if you immunize the population at a higher level, higher than this critical value PC, then you can expect either prevent the outbreak or eliminate the disease. And this PC is equal to 1 minus 1 over R0. So in many cases, the policies are sort of guided by this quantity. So the PC is the what was threshold? What's the, sorry, I skipped my mind. The population immunity threshold. Right? If you immunize the population greater than this quantity, right, you can control the disease. But when the heterogeneity is present, it's need to be considered, then this population immunity threshold is not as simple as this. It's not a single value. Suppose you have 2 subpopulations, either age groups or different spatial locations, then you will have infinitely many combinations of the vaccination coverage of the subpopulation to achieve that goal. And I'll present specific examples next. So when you consider multiple groups, multiple subpopulations, either by age or spatial location, then you will have this mixing pattern. This demonstrate, so you have n groups, and within each group, you have this SIR, for example, structure, or more detailed, if you have asymptomatic infections, or you have exposed, you have hospitalization, and so on. So within each subpopulation, you have this structure, but then those subpopulations can interact. For example, if you have multiple age groups, and they can interact through mixing. And this mixing can be important. So we usually, when you consider homogeneous mixing, then you can ignore the subgroups, right? You take some kind of average. if one subpopulation has a higher activity, for example, and then other has lower, then you just take average and then consider the single population with homogeneous mixing. But I will show you the issues with that simplifying assumption next. But first, more details about the mixing. One example, this earlier proposed by a Knott, published in the Mass Bioscience in 1980, and then this they call this preferential mixing, right? With this description. So basically, if you have a multiple subpopulations, group I and the group J, the mixing between those, so contact between those two subgroups can be expressed in this form. That group I will reserve epsilon I proportion of epsilon I between 0 and 1. So epsilon I proportion of the contacts will be reserved for contacts within the group I. And so delta ij is a delta function. It is 1 if I equal to j, and then 0 if I is not equal to j. And the 1 minus epsilon I, the remaining proportion of the contact, will be distributed among all groups proportionally. Okay, so A is activity level, N is the population size for the subgroup, and 1 minus epsilon I times aj, that will give you the unreserved sorry, it's blocking my view. Start my video. The host asked me to start your video. Oh, sorry, how can I get rid of this? Okay. I'm sorry. What?
Oh, sorry. It's just we were hoping that you can share your video as well, but if that's not possible, if it messes with the Zoom, then that's okay as well. Oh yes, now it's being shared.
I will try, but sometimes it may make things unstable. But if that happens, I'll stop. Okay.
No problem. Thank you.
Thank you. So the numerator is the total number of unreserved contacts for group J, and the denominator is a total number of unreserved contacts. So the probability that the contact for individual in group I with group J will be described by this proportion. So that's why they call it preferential, proportional mixing. This part is a proportional mixing, but the entire expression is called the preferential because epsilon I represent the preference of the group I, preference of contact to be with individuals in the same group. So this, when you have just two groups, and the mixing matrix will be given by the Cij, right? C11, C12, and so on, and then each entry is written this way. So you can still calculate this reproduction number analytically when you have just two subgroups. But when you have more, for example, sometimes you may have tens or even more than 100 subgroups, then this matrix can be very big and you can only rely on numerical calculations. And then, so how do you calculate those epsilon, right? The preferential parameters. And one of the papers we published, we use this data published by Mosong et al., but they use a social contact, sort of the survey data to represent how the transmission can occur based on those contact patterns. So this shows the age groups, like the age groups here and the vertical age groups, and how likely they contact, the frequency, and lighter color represent more contacts. So we can see clearly the main diagonal, more contacts will happen both within the same age groups. And they're also off diagonal. So those are the contacts between children and the parents. And there may also be preferential contact between children and grandparents. So we described this kind of pattern using mathematical representation. So this first one represents the main diagonal within same age group and the parents' children. And here also include children and grandparents. So this is published in the Math Bioscience in 2012. And to use those data to estimate the parameters in the preferential mixing I showed you earlier. And then you can see the comparison between observed context and the modeled. So after we estimate the parameters, they have a pretty good match. So we can use this kind of context matrix in our model. So the one I just show you, that's sort of more for age groups. But when you have a spatial, multiple spatial locations, then we can describe the mixing between location I and location J using this formula. This is just one of the examples. We discussed the several expressions, but this is the simplest one. And you can see how this is for the San Diego school district's data. Again, you can use the data to estimate the parameters in the mixing. And then once you get the mixing, you can apply the functional form and the parameter values in the disease model. Related to mixing, we have published several papers. I list a few here. As you can see, they're all in collaboration with John Glasser and other collaborators. And if you're interested in this topic, and I'll be happy to send you papers, PDFs. So once you have this mixing parameters estimated, function determined, and you can use those. So here, for example, see mixing matrix in the structured model. So this is an example of ODE systems, but includes both age structure, so index A represent age, and locations. So L represent location. And you can have this kind of standard SEIR model within each subgroup, a given age, a given location. But then all those subpopulations will be linked through this mixing, CLI, so LI-LP, so that gives you the interaction between location I and location P, and AJ-AQ, that will be the interactions between age group J and age group Q. And the one example can be in this form. Okay, again, we have considered multiple forms. So here you have the overall the context between different age groups and different locations, and then between age groups, and then you can have this looks like this preferential mixing I showed you earlier, except that the F function will be more complicated than the one I showed you earlier, because this would involve both location and age. Okay, so suppose that we have this mixing matrix determined and the parameter values estimated from data. Then, so what we can do is to analyze the model, right? For example, for the reproduction number. So what I would like to point out here is that in most cases that we considered, your reproduction number will have this, so the next generation matrix will have this form, and you can see the structure is that the AJ, so this given location, L given location A, so you'll have the structure. So those are the reproduction number for the group in isolation. Okay, suppose there's no interaction with others, just consider this individual group, then you have this reproduction number. And then, so kappa will be, if you consider other isolation or control measures. Okay, so that will be the sort of reduction or vaccination reduction in the reproduction number. And the typical feature is that the mixing C will be involved in the matrix in this form. So basically, the overall metapopulation reproduction number is the weighted isolated reproduction numbers, those R's, so weighted by the mixing, and in this form, right? So if you calculate numerically, and first of all, the analytic expression is not easy to get when you have the dimension higher than say 3 or 4, right? But if we have some kind of a proportional mixing, okay, I mentioned earlier proportional mixing, then this matrix will have rank 1. In that case, this dominant eigenvalue of this matrix will be the summation of the main diagonal elements. So in that case, we can have an analytic expression for the reproduction number. And in any other cases, then you will have to calculate dominant eigenvalue numerically. Okay, so now I'm going to talk a little bit about parameter estimation using data, either surveillance data or serology data. For example, so I want to remind you, in a model, so this lambda, this is what we call the force of infection. That's the transmission rate for susceptible individuals in particular group. And this lambda I, the force infection, involves those parameters such as activity level and probability infection per contact, and this mixing matrix, and the proportion of the subgroup that are that the individuals that are infected. So what we want to do is to estimate the force infection independent of the model structure. Okay, you can have like asymptomatic or treatment or isolation and so on. But this force of infection is independent of those. Sort of in terms of the connection between this transmission probability beta and this force infection. So if we can estimate this force infection using data, then we can estimate this probability transmission from that using this expression. And the A that we can get from the independent data source, right? For example, mixing pattern. And then this proportion of infection can be determined by the surveillance data cases in the given group. So we'll focus on this force infection, the estimation from serology data. So this here's an example. Suppose we have a proportion of population group. So now the A represents a subgroup with a particular age, right? And then 1 minus PI, so PI is immunization. 1 minus PI will be a proportion of the population, but susceptible, not immunized. And then the lambda is a force infection, and the E to this integral will give you the probability that the individual of age A is still susceptible at age A. So they skip the infection up to age A. So the whole thing here is the proportion of the individuals who escaped both immunization and the infection. And 1 minus that will be the proportion of people that carries antibodies, have antibodies, right? They have the virus either through immunization, either vaccination, or through natural infection. So this will be the serology data. It will give you this value. Okay? And then the connection between this data and the force infection is through this expression. Then if we discretize this, so most time your data will be discretized, right? Given age groups or given time periods or given locations. So if we do, we discretize it, assume that within each group, the force infection is the same. Right? Earlier when I showed you the ODEs, you do have the discrete force infection. And so this requires some kind of approximation, right? You assume within each group, they have the same kind of force of infection. Then if you do that, then you can derive the connection between the force infection and the serology S. And this is how we estimate the force infection, both in earlier examples and in the recent application to the US for SARS-CoV-2. And then once you get a lambda, so this is another example, so I'll skip because I'm spending too much time to explain this. So once you have a lambda, then you can get the transmission parameter beta, and you can apply those parameter values in the model. And, so here's another example using serology in a simpler case without immunization, just natural infection. Again, you have this connection between this probability of survived infection with the force infection, right? And the 1 minus PS will be the proportion of people that have antibodies. And then you can differentiate this one to get this attack rate and how the rate at which people get infected. And then using this relation between the force infection and the probability of transmission per contact. So A is the contact rate, Cij is the mixing, okay? And then you can estimate beta. So what I would like to emphasize is that this kind of parameter estimation is different from like a lot of people with the way they estimate parameter values is by fitting their model to data for surveillance for case data, for example, and then you get your parameter value. But for that, in that case, your parameter values will be dependent on your model, right? And if you change the model, you cannot use the same parameter values. But here we'll get the values specific to this particular disease, particular virus, right? And then you can apply it to different model structures. Okay, so now we go back to the model, right? Once we have a parameter values estimated, and we can do some analysis of the model. So I would here present the example with the just fewer subgroups, n equal to 2 or 3, to illustrate the approach of gradient, using gradient to identify the best vaccination strategy. So if you have a simple model, like just one structure, right, either age or location, not both. So when you have two structures, these models will be much more complicated. So if you do that, and you have this next generation matrix, again, you see this matrix involves individual regression number for individual group, and the mixing, Cij, right? And then the dominant eigenvalue will give you the regression number. And then, so we consider this preferential mixing that I mentioned earlier. Then, so if we have a two subgroups, okay. So here, I just want to show you that this individual threshold quantity, the single value is no longer good measure to use to determine population immunity threshold. So in this example, we have two subgroups, and the preferential, just consider a very simple case. Preferential level is the same for the group, both equal to 0.5. So 50% of the contact for that group will be reserved for contact with the others in the same group. Also consider same population size, N1 and 2. The only difference is in the activity level, the contact rate. Group 1 is 8, group 2 is 12. Right? So group 2 has a higher contact rate. But if you want to ignore the heterogeneity, then you make assumption that the total number of contacts will be 20 and then divided by 2. So each group has 10, right? That's the approximation. If you consider the homogeneous population, you'll have contact rate 10. Yeah. But if you consider heterogeneity here, and the two subgroups, P1 and P2, represent the proportion of the group immunized or vaccinated. So let's just assume their efficacy is 100%. So vaccinated is immunized. So you have a P1, P2, and then the RV. If RV is less than 1, right, you still have some combinations of P1, P2 such that RV, that's the reproduction number with the vaccination. If the RV is less than 1 below the blue plane, then you have the control of the disease, right? And then the curve here, intersection of the plane and the surface will give you the threshold combinations, P1 and P2, such that RV will be less than 1. So you can see there are even many combinations of P1, P2, right? So you cannot have just unique PC. Okay, but then the question is why does it matter, right? Single threshold or even many. So I'll show you in the next example. So this two curves, the two figures, shows the difference between homogeneous assumption versus heterogeneous mixing and heterogeneous contact rate. The curves, those are contour curve of the reproduction number. Okay, each contour curve gives a specific value of the RV. Okay, suppose that we have, so the first figure A, assume homogeneous mixed contact, both equal to 10, but the second one has a heterogeneous contact, 8 and 12, right? And then and the right curve correspond to RV equal to 1, right? And then to give you this best combination. So P1, P2 both equal to 0.74. So you vaccinate the population 74% for both group, and you'll achieve RV to be less than 1, right? If P1, P2 is greater in here, then your RV will be less than 1. But if you have heterogeneous structure in the population, given the same dose, same number of doses, so P1, P2, the proportion vaccinated, it's the same as the number of doses because N1 and N2 are equal, right? So if you consider the same so if you use the same number of doses, you actually will achieve the this value here, right? The RV, so you will achieve RV to be equal to 0.86, so this curve. So basically, you don't really need that many vaccine doses, right? To be equal to 1, you only need this combination of P1, P2, which will be fewer. The number of doses will be fewer than the twice of the 0.74. So basically the idea is, if the structure is considered, then the population threshold, immunity threshold, is no longer a good measure. Okay, so either you use more doses than needed, or you can achieve the same goal with a fewer number doses, vaccine doses. Okay, so that's just this very simple example to show you the importance of considering the heterogeneity or a structure in the population. Okay, so now how to identify that optimal vaccination combination, right, when the heterogeneity is considered. So the approach we considered, we call the gradient approach. So basically you have, so this surface of RV, right? Suppose current value is 4, and you want to reduce R4 to the RV equal to 4 to RV equal to 2, right? You want to achieve this reduction. And then what combination of P1, P2 you should consider to achieve that, to use a minimum number of doses, right? So P1, P2, so at this point you have the baseline value, and then you can calculate the gradient at the point given by this factor of partial derivatives. And then you want to find which direction, right? Which direction will give you, so each direction represents a combination of P1, P2. Which direction will give you the optimal strategy? And you go through the mathematics, the derivation, and you'll find that the gradient direction at that point will give you the best strategy. It could use the low, given the amount of reduction, you will need the minimum number of doses to achieve that. But you can also consider, given number of doses, you will achieve the most reduction. Okay, those two optimal strategies. That also consistent with this Lagrange, minimization Lagrange problem. Okay, so you have this regression number expression, and you have a fixed number of doses. C, so this expression gives you a total number of doses, the number of people vaccinated, and then you want to find the combination of ties that can minimize RV, right? And it turns out that that combination is really the gradient direction of the control curve, the RV function. Okay? So you can identify this numerically. Basically, this constraint line, dotted line, and the control curve, the that intersection, okay, that is the tangent. The line will be tangent, and then the gradient will give you the optimal combination. Okay, I think I need to go a little faster. For 3D, they use same thing, right? And you can extend this to any dimensions. It's just computations may be more involved. You have more subgroups. So when you have a lower dimensions, you can try to get the analytic expression of the reflection number. For example, in R+3, you can see it's already more complicated, right? When you have more than 3 groups, and this will be almost impossible in most cases to get analytic expression. But I just want to point out that there's an order for the regression number depending on the preferential level. Epsilon, that's again the proportion of the context reserved within a group, right? So this proportion, when it's equal to 0, that means you have no preference. I mean, that means that all your contacts will be distributed among other groups randomly. And epsilon equal to 1, then that means that all your contacts will be reserved with others within the same group. So we have an isolated population, okay? There's no interaction between subgroups. So for those R's as a function of the preferential level, epsilon, the order is this. So the RV reflection number is increasing with the value of epsilon. So basically, if you have a homogeneous population, your reflection number is the smallest. And then when you have an isolated population, the reflection number is the highest. Okay? When you have an isolated population, the reflection number is basically the maximum of all those sub groups reflection number. So this is very interesting results. Actually, the thesis of one of my students, her thesis is about this, right? They prove the existence and uniqueness of the optimal solutions when you have multiple subgroups. Considering the 2 optimization problems. One is the given vaccine doses minimize reflection number, or you want to achieve reflection number to be less than 1 and find the smallest number of doses needed. So under certain conditions on the mixing matrix, so see here's a mixing matrix, including the condition of essentially non-negative or irreducible and so on. And you can show that you have the existence and uniqueness of the solution, and which actually is the gradient direction as we noticed earlier. So what another interesting result is this, right? So she has different types of reflection numbers. In particular, this the harmonic mean of reflection number. Again, R0I is for group I, pi I is a proportion of the population in group I, and this harmonic mean is some kind of weighted average, but in this form. Okay? And then the order is, again, the minimized reflection number is between this harmonic reflection number multiplied by the proportion of susceptible, okay? because eta A is proportion vaccinated. And so this is upper bound, and lower bound is R tilde, and R tilde is this guy here. Okay. So it's not trivial kind of relations between the meta population reproduction number and the subgroup reproduction numbers. But you can see that you ignore the heterogeneity. So all activities AI are the same. Then each subpopulation will have this same. They all have the same reproduction number. In that case, the harmonic mean and this R tilde are the same as R0. So basically, they are all equal. There's no order, no difference. And in that case, you recover this earlier the threshold I showed you, right? When you have a homogeneous population, basically your effective reproduction number is the product of the basic multiplied by the proportion of subgroup. But if you have heterogeneity, and this no longer hold. Okay? And similarly, the threshold quantity. If you ignore heterogeneity, you recover the standard. But in general, you have more complicated connections between the population immunity threshold and the vaccination required. Okay. So I'm going to go quickly talk about two examples, recent examples. We use this approach I just mentioned in terms of mixing, the parameter estimation, and structure the population meta population model, and the gradient approach. So we apply it to the measles and the rubella in China. Okay, this is in collaboration with China CDC, US CDC, and WHO. We published two papers. One is on measles. It was published in International Journal of Epidemiology in 2019. Another one is about the rubella. This is published in the Lancet Infectious Diseases 2021. So I'll just show you quickly the applications. Okay, this is the model I showed you earlier, right? The model with the two structures, age and spatial location. So in China, there's 31 provinces and other districts. And those are spatial structure, and then within the age structure, for measles or rubella, childhood diseases. And we know that your vaccinations, you vaccinated newborn, right? Newborn and an 18-month-old. But later on, because those vaccines are, those schedules are not eliminating the measles in China, even though measles have been eliminated in many places in the world, but not, China still has a lot of cases. So they want to develop some kind of vaccination strategies to accelerate the elimination of the measles and rubella. So that's how we start working on this project. So I already showed the model earlier, and the important thing is a mixing here. And then we also estimate the parameters using surveillance and the serological data from China. And then we use the gradient approach. So we get the reproduction number, both basic and the effective reproduction number. So we consider 3 regions in China: Central, East, and the West. Right? And so when you look at the gradient calculation, and you can see that because gradient give you the contributions of the subgroups, right, either age or spatial location, the contribution to the reproduction number. So we can see that the younger age group will have a higher, sort of more influence, more contributions to the reproduction number. And you can also look at this map, both R0 and RE. So this is for individual locations. And you can see the magnitude, right, with different locations, different populations. Oh, sorry. Okay, and then if we use those information, right, you identify through gradient calculation, you identify the key groups, the groups that contribute more to the prevalence, to the disease cases. Then you can focus on those groups, target those groups for the vaccination efforts, right? Both age groups and spatial locations. So if we do that and then we compare those strategies with the current, if you apply the current strategy versus the optimal identified by the breeding calculations, and you can see how long it will take, how many years it will take to eliminate the disease. Elimination means that you have lower 1 case per million, right? You can see how many years it will take to eliminate under different coverages, right? You buy some 5%, 10%, 50%, and so on. You get different strategies. And so what I would like to point out here is this so-called indirect effect via mixing. So we know that, showed you earlier, the younger groups, adolescents, they tend to have a more influence or more context. And then if you focus effort on those groups, so you will reduce the cases not only in those groups, but also in other groups because of the context, the mixing. Okay. So that's indirect effects. So we can see that if you, vaccine certain percentage of the population, the adolescents here, and how much the effect within those groups versus and the total population, right? So those are two different strategies. One is focusing on the adolescents, one is focusing on adults, because when they observe that the cases, a lot of cases are occurring in adult groups, because maybe some adults, they did not get vaccinated when they're young or at birth, so later on they got infected, right? So maybe that intuitively you should focus on those groups, right? The groups that have more cases. But in fact, if you focus on younger groups that have more contacts, then the effect may be even better. Okay, so those are the comparisons when you focus on adolescents versus focusing on adults. Okay, either achieve same goal with fewer doses, or given number of doses, you can reduce the cases more, or you eliminate the disease in shorter time period. Okay, so this again shows the importance of considering structured population models. Okay, because if you use a homogeneous mixing, use a single group model, you will not be able to get those results. So just quick comparisons for the measles and the rubella, okay? And this optimal strategies, right? This is for eastern provinces, and so we can see a little bit of difference between measles and rubella. Even though MMR, right, that's the vaccine that works for 3 childhood diseases, measles, rubella, and the mumps. But we can see when you focus on different subgroups, then you may have different outcome, right? So here, rubella, we can see this sort of, we should target more on the adolescent, right, the younger groups. But for measles, the age groups are a little higher. Okay. Similarly, for other central provinces, similar pattern. For the western pattern, also western provinces, also similar. Okay, so what we observe is that we can, for the rubella, we should focus on younger groups, more on younger groups, but because younger groups have more contacts, right, are more active, and they have the higher indirect impacts. So even though they may not be optimal for measles, but they can still accelerate the elimination for both rubella and measles. So again, so I showed you example for other diseases and other populations instead of SARS-CoV-2 in US population, but the ideas and the approach of the modeling approach and analysis are similar when we apply serology data for the US populations and apply to the vaccination strategies in the US population. And again, hopefully the paper can be published soon. So I'll stop here and now, oh, actually I do have one slide here, preliminary results. Actually, this is from earlier presentations, and now we already have new results that will be published in the paper. But this is just example for US population. This using the serology data. And again, we use this structural model structured by age and spatial location, so different states, or 51 states. And then you get this reproduction number, R0, and then you can calculate the contribution of the both age groups and the different states, the contribution of subgroup to the reproduction number. So you can see which group has more influence and which state has which states have a higher contribution to the R0. Okay. So the ideas will be similar for effective reproduction number of equilibrium distribution and so on. And then we also compared the vaccination strategies, right? Because for US, they focus on the elderly first in the beginning, when they have limited number of vaccine doses available, and then later on expanded to different age groups, right? So what if we, consider the vaccination strategy based on, say, gradient calculation for the US population, how different the outcomes will be, right? We'll make those comparisons. But those will be in the paper. I cannot talk in detail here. Okay, so now I'll end here. If you have questions, and I'm happy to answer. And also, I'm very happy that John's here, and he can also help answer any questions.
Okay, so first, let's thank the speaker for a very nice, interesting talk. And any questions? You can hear us, right? Zhilan, can you hear me?
I can hear you, yes.
Yeah, sure. Any questions? Any questions? Yeah. Could you please